All right, so let's take a look at section 4.2. So in section 4.2, we get into logarithmic functions, which is another branch of functions that go hand in hand with the exponential functions we talked about the other day. The relationship between logs and exponential functions is that they are inverses of each other. If you remember back to chapter 2, the end of chapter 2, we talked about finding the inverse of a function. So logs and exponential functions are a special group of functions that are inverses of each other. This definition here is how we can go between the two forms. So y equals log base b of x can be expressed as b to the y equals x and vice versa. This definition is very, very important. You're going to use this all through the rest of this chapter, and it's really, really essential that you understand how to apply this definition to convert between the two forms, log and exponential forms. So let's do some practice here. It says write each equation in its equivalent exponential form. So first notice that these are in log form. We want to switch them to exponential form. We're going to use this definition to do so. So the way I kind of think about this definition is I always start with the base, whatever the base is, log base b of x. That's base b is what I'm interested in. And I always think of it as b raised to the other side power equals whatever's inside the log, whatever's inside the argument, and that's what gets you to this form, b to the y equals x. Let me show you down here. So we've got 2 equals log base 5 of x. Start with the base. What's the base here? The base is 5, so I want it to be 5 to the other side power, so 5 to the second power equals the argument x, and that is equivalent exponential form. You don't have to change it to a 25. I don't care that it's 25. I just want it in exponential form. So 2 equals log base 5 of x is equivalent to 5 to the second power equals x. Let's try another one. 3 equals log base b of x. Start with the base. So the base is b, right? So we're going to go b to the other side. So b to the third power equals what's inside the log, equals x. So b to the third equals x. The last one, they've written the log on the left side instead of the right side. It's the same thing. Don't let that throw you. We're still going to start with the base. What's the base here? The base is 3. We're going to raise it to the other side. So 3 to the y power equals what's inside the log? 7. So 3 to the y equals 7. Now, in example 2, they want you to go in the other direction. They're starting in exponential form, and they want you to go back to log form. I always start by writing the word log on my paper, so log. And so we want the base, log base b. So b is whatever the base is for your exponential function. So log base, what's the base here? 12 of the other side. So it's still, you go of the other side, so of x equals what's in the exponent, 2. Log base 12 of x equals 2. The notation for these is very important. The base, that 12, is a subscript, so you have to have that there as the base. X is the argument, so it's on the same level as the log. So log base 12 of x equals 2. Try the next one. Log base, what's the base? B of the other side, 8, equals the exponent, so equals 3. Log base b of 8 equals 3. The last one, start with log of the base is e, of the other side, I just threw the of in there, sorry, log base e of the other side, 9, equals the exponent, y. So this is log base e of 9. Now normally, remember we talked about e the other day. E was that natural exponent, 2.718 something. We normally don't write log base e. That would be okay to write that, but the shorter hand way of writing that is to use ln. ln is the natural log. It's a Latin word, Latin root word, but it's natural log, ln, of 9. So if you have log base e, replace it with ln in your final answer. And when you do that, there's no base to write. It's an implied base e because of the ln. So that would be the proper answer. Now there's a few log properties I want you to be familiar with. We're going to use these throughout this chapter, so get comfortable with these. The first one is called the identity rules. Log base b of b equals 1. Log base b of b equals 1. So if the base and the argument are the same, that just simplifies to 1. log base b of 1 equals 0. So it doesn't matter what the base is. If you're taking the log of 1, it's always 0. The inverse rules, log base b of b to the x power, so that you can kind of think of this, because remember there are inverses, you can kind of think of them as canceling each other out. The log is undoing the base of the exponent, and it's just leaving you with the exponent itself. And then the other inverse rule, b raised to the log base b of x equals x as well. A couple other things to note when you work these problems. When you see log log of x and there's no base, that's an implied base 10. It's kind of like when we write a square root sometimes. If I say square root of 9, for example, we know that's a 2, even though we don't write it. So it's the same idea. If I have log of x, that's an implied base 10, and we call that the common log. That's an important one we're going to see a lot. And then like we just talked about, ln is the same as log base e, the natural log. So let's use some of these properties to evaluate the questions in this section. So the first one we have is log base 7 of 7. So look back at your properties. The base and the argument are the same, log base b of b. So we're using this identity rule. So log base 7 of 7 just turns into 1. Letter B, log base 3 of 9. So if I could rewrite 9 as a power of 3, I would be able to apply this inverse rule right here. You notice that 9 is a power of 3. So I'm going to write 9, I'm going to rewrite this as a power of 3. So it's going to turn into log base 3 of 3 to the second power. Make sure you see what I've done. I replace the 9 with 3 squared. And why does that help me? Because the base and the argument are the same, so I can apply this rule right here. Log base b of b to the x just simplifies to x. So what is this just going to simplify to now? And that would be 2. Letter C, log base 25 of 5 equals what? So we're going to use the same idea. If I can rewrite 5 as a power of 25. Now you got to think back to what we did earlier in the course. I want to write 5, so 5 raised to some power. We know that that's, let me say that again. We know 5 squared is 25. But here's my question. We want to write 5 as a power of 25 because 25 is the base. So let me try that again. 25 raised to what power will just give you 5. And if you remember back earlier in the course, we said that if we use a fractional exponent, that's the same as the square root. So remember 1/2. 25 to the 1/2 power was equal to 5. You remember that because that was the same as the square root of 25. Remember 25, anything to the 1/2 is the same as the square root of that number. So what I'm going to do is I'm going to replace this 5 with 25 to the 1/2 power. So I have log base 25 of 25 to the 1/2 power. So now I have the same base and the same argument. So I can apply this inverse rule up here, and that just leaves us with 1/2. And that's it. Letter D, we have log, common log, log of 100. There's no base there, so we know it's an implied base 10. So how can we rewrite 100 as a power of 10? I'm going to write it as log base 10 of 10 to the second power. And so now, applying the inverse property, log base 10 of 10 squared just leaves us with 2. Let's try the next example. Log base 2 of 16. Can we rewrite 16 as a power of 2? I realize 16 is 4 squared, but that doesn't help me because the base is a 2. How can I rewrite 16 as a power of 2? In other words, 2 to what power? Gives me 16. And that would be 2 to the 4th power, right? 2 times 2 times 2 times 2. That would be 16. So now this is log base 2 of 2 to the 4th. I just replaced the 16 with 2 to the 4th, so that just leaves me with 4. Log base 5 of 1 is the next example. Log base 5 of 1. Okay, log of 1, does not matter what the base is always 0. So that's it. Nothing else to compute there. Letter C, we've got log base 5 of 4 to the 5th power. So that's a direct application of this inverse rule. Log base b of b to the x equals x. So log base 4 of 4 to the 5th just leaves me with 5. Letter D, 6 raised to the log base 6 of 9. What does that leave me with? So that's an application of this property right up here. So that just leaves me with 9. Example 5, we want to simplify. We have natural log of e to the 7x. What you need to remember is that natural log is really what base? Natural log, remember, is base e. So this would be like saying log base e of e to the 7x. That's what they're asking you to simplify. Well, because the base and the argument are the same, we're back to using this property right here. Log base b of b to the x equals x. So log base e of e to the 7x just leaves us with 7x. You don't have to write this every time. I just want you to see that natural log is the same as log base e. So that's why that just simplifies to 7x. Letter B is the same idea, e to the natural log of 4x squared. E and natural log are the same base, so that just leaves me with 4x squared. Letter C, natural log of e to the 25x. This is very similar to letter A. What is that just going to simplify to? Since natural log of and e are both base e, just leaves me with 25x. And then the last example, e to the natural log of the square root of x. I'm applying this inverse rule right here, b to the log base b of x equals x. So this just leaves me with the square root of x. All right, so the second sort of big topic for this section is graphing logarithmic functions. So we're looking at graphing the basic logarithmic functions. It's very similar. The shifting and the rules are very similar to what they were for exponential functions, but you'll notice a few key differences here. First, let's talk about what the basic log graph looks like. So it's, let's see, let's make a quick little sketch here on our paper. So we've got our x-axis and our y-axis. And it's going to be an increasing function the entire time, just like the exponential function is. However, instead of going through 1 on the y-axis, it's going to go through 1 on the x-axis. So it's going to have an x-intercept of 1, and it's going to be increasing just like this. So regardless of what the base is, or there's a certain condition here, whatever the base is, for the basic log function, it's going to look something like this. It's going to be increasing the whole time, goes through 1 on the x-axis. The domain would be based on, look at your graph, the left and right, remember x values are your domain. The leftmost x value, it never goes past the y-axis. So think about what your domain would be for this. It doesn't go below 0, and it never actually touches the y-axis. So I'm going to put parentheses around the 0, and then it goes up to infinity. Range is from negative infinity, because the arrows goes all the way down to negative infinity and up to positive infinity. Y-intercept, there is none. And then the x-intercept is at 1, 0. Horizontal asymptote, this time there is no horizontal asymptote. However, there is a vertical asymptote. It's the y-axis, so the vertical asymptote is x equals 0. Now, as long as the b is greater than 1, so as long as the base for your log is greater than 1, you're going to have an increasing function. Again, I'm not so concerned about what the b itself is, as long as if it's positive, or I'm sorry, if it's greater than 1, you make it an increasing function. If it's between 0 and 1, you're going to make it a decreasing function. And we're not going to get really complicated with these graphs. I just want you to have a basic idea of what they look like. And the b, just like it did with exponential functions, the base affects the steepness, but I'm not so concerned about how steep you make them as long as you have the right basic shape. The transformations, though, are the same as they were for exponential functions. So if you've got log base b of x, where x is your argument, and then the plus c or minus c is on the outside, that shifts the graph up and down. If the plus or minus c is on the inside in your argument, that's going to shift it left and right. There's your horizontal translation. And just like before, remember with horizontal translations, it's opposite whatever the sign is. If there's a negative in the front of the log, it's going to reflect over the x-axis. And if the negative is inside the argument in front of the x, it's going to reflect over the y-axis. And again, the c is going to stretch the graph if c, so if you're multiplying by a constant c in front of the log, it's going to stretch the graph if c is greater than 1. It's going to shrink it if c is less than 1. And the main thing to remember here is it changes the x-intercept. We're not going to do a whole lot with these. I just want you to have your notes complete. Let's look at a couple of examples, though. So f of x equals 2 to the x. They want us to start with a graph of 2 to the x. Well, that was our exponential function from the last section. So remember, the exponential functions go through 1 on the y-axis. So it's going to be increasing on the y-axis from left to right, just like that. So there's 2 to the x. Now, log base 2 of x, okay, so it's going to look just like this one up here. It's going to be an increasing function since the base is positive. Or I'm sorry, since the base is greater than 1. It's just going to go through 1 on the x-axis. And there you go. You may or may not remember from back in chapter 2 when we talked about inverses. We said that one characteristic of inverse functions is that they're reflective of each other over the line y equals x. And these are an example of what we were talking about there. Over the line y equals x, these are a reflection of each other. If you take this graph and you flip it over that line, you'll get g of x. And that's because they're inverse functions. Take a look at example 2. They want you to graph log base 3 of x. So it's going to look very similar. If you want to make it a little steeper, but not really a big deal, it's going to go through 1 on the x-axis. So there is f of x, log base 3 of x. Now, how is the x plus 2 going to shift? It's inside the argument, so that's going to be your horizontal shifting. Remember, it's opposite whatever the sign is. So if it's plus 2, it actually is going to move it left 2 units. So take your x-intercept and count to the left 1, 2 units, and there's your new function. Now, because this shifted horizontally, what else also shifted with it? We have a vertical asymptote, remember, at the y-axis. So if I move everything to the left 2 units, that vertical asymptote shifts as well. So go ahead and draw in the new vertical asymptote. If it was at x equals 0, now where's the new vertical asymptote going to be? At x equals -2. And then the last example, we're looking at our natural exponent function and our natural log function. Those are inverses of each other because they have the same base e for both of those. So the e to the x goes through 1 on the y-axis, and it's an increasing function. So there's e to the x. And then the natural log of x is going to look like our other log functions. It's going to go through 1 on the x-axis. These graphs are not all that exciting, I don't think, but I want you to see, though, we have that inverse property again, that these two functions are inverses of each other, so they would be reflective. You don't have, this isn't part of the graph, but if you want to draw it in, you can. They would be reflective over that line y equals x.